we still have that, but now we say the beta 1 and the beta 2 are themselves functions of characteristics of these regions, characteristics of the regimes. And in fact, we use the variability across the beta 1, beta 2, and so on to come up with a model for that variability. And that then gets substituted back in our equation, very much in the same spirit as the expansion method. So we have these additional error terms. Now, the difference between this and the expansion method is that here, the error term is at the scale of the states. So this is a state-specific error term. In the expansion method, the additional randomness that we introduced was at the same scale as the original variables. Here it's at a different scale. So the original observations, the ij's, have an ij error term, which is individual specific. These equations, if you wish, expansion equations, have an error term which is at a different scale. It's at the high, that's why it's called multi-level. It's at a different level. So this error term, for example, could capture spatial autocorrelation between states. The error term with the ij index could capture spatial autocorrelation between counties. So you could have an equation that says my slope is explained by these state characteristics, but not completely, and there's spillover between the states. So therefore, this error has spatial autocorrelation in it. And that's where it gets interesting, because we substitute this back into the original equation, just like we did for the expansion model. So we have something that is contains a lot of interaction effects. But the interesting part is now the interaction effects combine scales. So the interaction effect of xij and z2, for example, the xij is a county-specific variable. The zj is a state-specific variable. So all the counties in the same state get multiplied by the same z2 because it's state-specific. So it's a little, formally it looks exactly like the expansion method, but conceptually there is a major difference here in that we are mixing multiple levels. And some of these variables have variability at the county level, and some of them only have variability at the state level, which means that you can think of this almost like a step function. All the counties in the same state get the same z, but the same z is multiplied by different xij's, so in the end, it varies. It's not constant like a dummy variable would be. The interesting part is in the error term, because the error term now contains this psi error from the constant part and the psi2 error, which is multiplied by the x variable, and the original error, the epsilon ij. So we put them all together. Then we have three, in this very simple model, three components in the error. And look at the indices, at the subscripts. The epsilon is easy. The subscript is ij. So in our example, this is a county-specific random aspect. Then the psi's have a j subscript. So these are state-specific random components. So then the question is, what is the covariance structure? Are these independent? Are they uncorrelated? Or are they correlated? Typically, the random components associated with different parameters are correlated. They have a covariance matrix. The question is then, are they also correlated with the random component at the individual level? And from our point of view, and I didn't write this out because it gets incredibly complicated, is where do we introduce spatial autocorrelation? Because we can introduce a spatial error process at either one of these levels. And this is just a two-level model. You can think of higher levels as well. You can think of counties, then somehow districts like development districts or planning districts, which are aggregates of counties, and then states, so you have multiple levels. And a priori, there is no reason why one level would have spatial autocorrelation and another level would not. The tricky part is identification. You can't have it all. If everything is spatially correlated with everything, you will not be able to distinguish the effects. But typically what is done in these kinds of models is that or at least in the applications that I've seen, is that the spatial autocorrelation is introduced at the higher level. So you would have a spatial process applied to the statewide error terms, and that would then be reflected in a very complex covariance structure for the error term. Now, how do we estimate these? It is a problem of a non-spherical variance-covariance matrix, so immediately we think feasible generalized least squares. As it turns out, it's not that easy because we need to estimate these variances and covariances from residuals. That's really the only information we have. In some fairly simple cases, we can write out the maximum likelihood, but typically we can't. And the methods that are used are iterated feasible generalized least squares. So basically, you start with a model, you get residuals, you use these residuals to get estimates of the variances and the covariances between the different parts. You stick that back in the model, you re-estimate it using feasible generalized least squares, you get new residuals, you start the whole process over again until it converges. For the real complex models, that even doesn't work, and you have to resort to Markov chain Monte Carlo, which is a simulation estimator.
So are those more complex models spillover models?
They could be, yes. And the substantive question is, where do you introduce the spillover? Do you introduce it at the micro level, or do you introduce it at the macro level? And when you have more than two levels, then it gets even more complicated. It really becomes an issue of tractability in the end. And identification problems are really serious in these models because they're not about the variables themselves, they're about the error terms. So error terms are not observable. We have residuals, and from the structure and the residuals, we're trying to extract these components of the variance or the covariances. And this is a classic example where you can get negative estimates of a variance. If you don't force this non-negativity constraint in the estimation, you take some residuals, you take some part out of the residuals, and there's no guarantee that that part will be positive. And that's what happens in these kinds of models.
So the MCMC and the HLM and those packages, don't they just deal with spatial error? This is really my question.
They don't deal with spatial lag. Is that what you're
Yes.
asking? Yeah, no, they don't.
Yeah.
And this is, and I mentioned this to somebody yesterday, this is a tension between spatial econometrics and spatial statistics. In economics, the model of spatial competition is a very meaningful model. So the spatial lag as an expression of that model, or if you wish, of the equilibrium outcome of such a competitive model or a game theoretic model, has a lot of appeal as a model. To statisticians, it does not. Statisticians tend to focus, and I've had this discussion with Noel Cressy, where he points out that there is a model for the main structure, and then there's no place for these spatial effects in there, and then there's a model for the error, and that is where we put in the micro-scale variability, which is where the spatial effects come into play. So there is a little bit of tension between these two ways of looking at the world, and most of the multi-level work and also the Bayesian hierarchical work has come out of the statistics world, has not come out as much, nearly as much, in econometrics. So the focus has been on modeling error structures. And I mentioned this in other conversations yesterday as well. What if the dependent variable is a count? Then you have a Poisson regression type of situation. How do you deal with spatial effects in those? The typical approach is again to model it as an error component structure. So you have some random component that you introduce in the error term in which you introduce a spatial process of some sort, typically a conditional one, and then you estimate this by MCMC because there are no analytical solutions. So again, no spatial lag. Okay. So if we're interested in substantive interaction processes in a cross-sectional situation, there is no, or not yet, a way to deal with that in these contexts. Now, it's not impossible to do a spatial lag model in a multi-level context, but it's going to be very complicated. I mean, these, if you look at the literature, these models, the multi-level models with spatial effects in them, are already incredibly complicated. And so, in addition, you're introducing the spatial lag, which in essence makes everything simultaneously dependent. And I suspect there are very severe identification problems.
The example that you've given, has a higher level that completely contains the lower level, counties within a state. What if you have a lower level that's split between a higher level, or thinking like census tracts and zip codes, where there may be multiple tracts within a zip code?
Okay, that doesn't quite fit in this framework. And this is a problem of what statisticians call change of support. So what it means is that the spatial container changes and doesn't match. So the counties add up to states, but say census tracts don't necessarily add up to school districts. Okay, or to, I mean, they do in election because they have to, but school district, water management districts, various types of policy districts, metropolitan transit authorities, they all cut through these things. So then the multi-level doesn't work because the levels do not add up. And however, there obviously is some kind of aggregation going on. So this is dealt with from a Bayesian perspective as a hierarchical model, where in essence the data as well as the parameters, everything is random. So you're dealing with this as a simultaneous estimation and prediction, which in the Bayesian context is a natural thing to do. In a classical context, that's a lot harder to do this. And so you try to find the best match, if you wish, between the interpolated values in the scale that doesn't match and the parameters of the models that you try to estimate. In the classical approach, what you would do is a two-stage process. First, you would interpolate. You pick one as the scale of analysis. Let's say you want to do school districts. And then you figure out a way to turn your census tracts into school districts. And this is a problem of spatial interpolation, of area-to-area interpolation. And the traditional solution, and also the one that is unfortunately the default in most GISs, is area-based weighting. So you reallocate, say, the population or the income of census tracts to the new container based on the areas of overlap, which assumes a uniform distribution in space. So anytime you go away from this uniform distribution, then the areal weighting is no good, and then you have to come up with some other weighting technique. That's me, I just ignore it. Just crank call. So that is a tricky problem. There are a number of solutions that deal with the two-stage approach with the interpolation. The most elegant solutions are the ones that are couched in a Bayesian hierarchical framework. And I haven't seen these applied to very large problems, but they've been applied, for example, to problems with you know, air quality and health measures where you have census tract data and then different scale measures for the air quality. I can give you some references if you